All right, this is our first video in integral equations. So in the first video, we will be discussing about the definition of an integral equation. We will know what an integral equation is, and then we will classify it into various types. Before we jump into the classifications, we first need to understand what an integral equation actually is. So right now, I will write an equation on the board. U of x equals to f of x plus lambda per x t with t dt. So I have written an equation here. U of x equals to f of x plus lambda integration of k of x t u of t dt. At first, we don't know what they actually are. Okay, what is f of x here? What's this? U of x? What's lambda? We don't need to know. Okay. So let us consider this u of x to be our unknown function. It can be anything. It's just an unknown function. If we look at this equation, we can see that this function u of x also exists inside this integration sign. It exists here as u of t. So the unknown function also exists inside the integration sign is known as integral equation. So the question may arise, what is f of x? What's lambda? What's k of x, comma t? And why do we even use t here instead of x? To answer the last question, the reason why we use t here is not of a big deal, because this is basically just a dummy variable. And we use this t instead of x. We could have used anything. We could have used y. We could have used alpha. We could have used xi. It doesn't make any difference. But we use like this type of dummy variables inside the integration sign is to make the calculations. When we do the maths, we will do it later on. It doesn't clash with anything, and it doesn't cause variable clashing. So we use t. We could have used this. We could have used anything. We could have just used like even Bengali scripts. It doesn't make any difference. So we use t because it's just a standard, and you will see in many textbooks it's written as such. In older textbooks, probably they used to use this Greek letter. I just forgot its name. And when we do the math, and finally we plug in the limits, g of x to h of x, it does have a limit, and it's very important. We'll see why later on. When we plug in the limits, the t or any dummy variable just vanishes, so it doesn't matter. So we understood that the unknown function, if it exists inside the integral sign, it is called an integral equation. Right now, before I explain what these are, I'm just going to write the definition. This is an integral equation. The next question arises about these terms. What is f of x? What's lambda? And what is this k of x, comma t? What are these? This is a general equation. This is just a generalized form, okay? Let me write it here as well. This f of x is just an arbitrary function. Like it's known to be called free term. And it's just an independent function. It can be x squared, it can be sine of x, it can be anything. It can even be a constant number, like 5, 7. It can be anything. It doesn't make any difference. So this is a preterm, and that it is not related to this unknown function. This lambda here is known to be a parameter. It's a parameter which scales this whole integral. This k of x is a special one. It's known to be kernel or nucleus. In most cases, we just use kernel. And this is very important, and it acts as the backbone of this whole integral. This u of t is the unknown function. This is the unknown function that we talked about. And this is just the dt. It's fine. This is the lower limit, and this is the upper limit of the function. Okay? The limits are very important here because based on them, we classify this integral equation into various types. These limits can be constants or they can be variables. They can be a function of x itself. So, as we said, we classify into various types. When the limits g of x and h of x are constants like a, b, or anything, then it's called a linear integral equation. Sorry, I just introduced a new term. It's integral equation of first kind. Oh, sorry, not first kind. Damn, yeah, I just forgot that. It's called a Fredholm integral equation. This is Fredholm integral equation. When the limits g of x and h of x are constant, then the integral equation is called Fredholm integral equation. If the limits g of x, h of x are variables, like they're a function of x, like x squared or something, then it's called Volterra integral equation. They're just names of integral equations. We don't need to be so super curious about what Fredholm or Volterra is. It's like the names of the integral equations. So, pardon. The first case, Fredholm integral equations, it looks like this. It's the whole same thing because we have lambda, but the limits are constants. So it's from a to b, k of x comma t, u of t dt. And second case, it's just like this. In most cases, practical usages, just the upper limit is the variable one and the lower one is basically a constant. It can be anything. So in most cases, even if it's variable, it's Volterra equation. But in most cases, it's the upper limit which is variable. So it looks like this. H of x here, k x comma t u t dt. So we saw that there are two types. Fundamentally, two types of integral equations depending on limits. We can also classify integral equations into various types depending on the existence of unknown variables outside or inside, or even the existence of the free terms, if it exists or not. So we will see that if f of x equals to 0, that means this term simply does not exist, then it's called a homogeneous integral equation. So if f of x equals to 0, the integral equation will look like this. Just going to write the generalized way. K of x comma t ut dt. So this is called homogeneous integral equations, okay? This is the structure of homogeneous integral equation. And if the f of x is not 0, so the f of x is not 0, there is some terms outside the integral sign at the right hand side, then it looks like this, which we wrote a few minutes ago. And this term is known to be non-homogeneous. We call this to be non-homogeneous. integral equation. And depending on the existence of unknown function outside the integral, we divide it into two types as well. If the unknown function only exists inside the integral, then it's called integral equation of first kind. If the equation looks something like this, we put in the limits here, and then we write the kernel. We see that the unknown function is just inside the integral, and there is no u of x outside, which we used to have before. If this is the structure, this is known to be the integral equation of first kind. And if the unknown function exists both inside and outside the integral, because to be an integral equation, it is basically a requirement that the unknown function must be inside the integral. So if it exists outside the integral as well, then we call it to be the second kind. And it basically looks, again, like the thing that we wrote a few minutes ago. It's just the same thing. This is known to be the integral equation of second kind. Integral equations can also be classified into linear integral equations and nonlinear integral equations. A linear integral equation and nonlinear integral equation, the key difference is the power of the function itself. If the power of the unknown function is 1, then it will be a linear integral equation. Like if we write u of x equals to f of x plus lambda, and then the rest of the thing, as we see, the power of the function is 1, even inside the integral. So if it is 1, then this is known to be a linear integral equation. However, if the power of the function is not 1, if it is greater than 1, or if it is trapped inside another function, whether it's inside or outside, it doesn't matter. If any of the one unknown function is trapped inside another function, or if the power is not 1, then it's called a nonlinear integral equation. And examples of nonlinear integral equation can be written, for example, this g of x, h of x, k of x, t, u, t, dt. This is a nonlinear integral equation. Even this one, for example, or let's just keep them as like this, xt, u, t to the, let's say, third, dt. This is a nonlinear equation because the power of the function inside the integral is not 1. Even though it is 1, any one of them, if the power is not 1, then it's a nonlinear equation. Or if it is trapped, like inside a function, then it's also a nonlinear integral equation. If the function is trapped inside another functions, even if it is inside, it doesn't matter, it's nonlinear. However, a key distinction to make is to remember that I said the power of the function. I didn't say the power of the variable. If the variable doesn't have, like if the function is of power degree 1, but the variable is squared or anything, and the equation looks something like this, this equation is still linear because the degree of the function itself is 1. No matter what the variable is, if the degree of the function itself is not equal to 1, then it's called a nonlinear function, nonlinear integral equation. But if the degree is 1, then no matter what the variables are, it's just linear integral equation. So this is the type, this is the whole type we will discuss till now, and this is the first video. Later on, we will be discussing how to solve this. The target, the main objective here is to solve for u of x. We need to find the answer, and we will do anything to get the job done, like on h of x. We will use Taylor series, Laplace transforms, etc., to do the maths. And as we said, also in some case, this thing is of nth degree, like nth derivative. So we will just know how to solve with the weird nth stuff and get the u of x. We do not solve for u of nth derivative of x, of course. We solve for the u of x. So this is it. This is the first video. And from the next video, we'll be discussing about the topics. Thank you so much.